Thermal modeling in Ruby. The scenario is months of DTS data captured in Emerald from a producing well that has been affected by an advancing waterfront from an injector. Some perforations see the cool front more clearly than others. Using Explore, it is possible to see the temperature evolution versus time at various depths. Temperature first increases and then decreases, and the behavior changes with depth. Now display traces versus depth. At the start of production, before water breakthrough, the temperature profile indicates fluid inflows from the perforations that would be expected for a multi-layer liquid producer. At some point, a temperature drop is seen at the second perforation. Above this depth, the temperature continues to increase. Situations like this cannot be modeled by analytical means, as offered by Emerald. DTS alone does not provide a hold-up measurement, which is absolutely necessary for multi-phase calculations. Also, the presence of non-geothermal inflows and strong transient effects require a different type of modeling technique. Ruby, the three-phase numerical simulator, which is an ideal tool to build proof of concept or what-if scenarios, will be used here. Run a simple simulation with an injecting and a producing well. Check that the temperature modeling option is selected. The reservoir description comprises 4 layers with thickness as defined here. Three of them will have constant reservoir parameters, although one of them is assigned a permeability 3 times higher than the others to try and simulate the early water breakthrough and possible cooling observed in the DTS traces. It is necessary to define the geothermal gradient. This info may be extracted from the traces in Emerald. The definition of the 2 wells can be seen here. When modeling temperature, it is necessary to define an intake model, including the heat loss coefficient. In this scenario, a constant oil production of 9,000 barrels per day and water injection of 8,000 barrels per day respectively are assumed. Next, initialize the model. As well as the typical well gauge outputs, the production logs of the producer and injector will be generated. These will include the temperature simulations. 60 logs will be generated. Run the model for 60 days, 1 log per day. In the well results plots, show the water breakthrough after 1,000 hours. Looking at the temperature logs, it evolves pretty much as would be predicted by the Ramey equation. There are no indications of cooling even after the breakthrough. Look at the map showing the saturations and pressure distribution. At the end of the simulation, it is clear that the waterfront has reached the producer well. Look also at the temperature evolution in the reservoir. The cold injection water starts to cool near the wellbore, and then progressively the reservoir cells between the injector and producer. However, by the end of the simulation, the thermal front is still far from reaching the producer. Hence, the saturation and thermal fronts do not propagate at the same speed, which is given by the permeability and thermal conductivity respectively. A different scenario may be run quickly. Simulate the presence of a fracture connection between the wells. This is a situation that can typically occur when the injection pressure goes above the fracture gradient, also known as channeling. Go back to the map, zoom between the two wells, and draw a fault that connects the producer and the injector. Define the fault parameter per layer, selecting an infinite conductivity fracture in Layer 3 where cooling is seen. The other zones will be kept as leaky faults. Now rerun the simulation. The only difference to the previous case is the addition of the fracture connection. As a consequence of this, the water breakthrough occurs earlier. When displaying the temperature logs, the evolution is similar to before, but now, as soon as water breakthrough is seen in the water rate log, the temperature starts to drop as a consequence of the fracture. This corroborates what was seen in the DTS traces. Again, going to the map, this can be seen in the temperature evolution, although this time the cold front reaches the well. This concludes this video on thermal modeling in Ruby.